Hi, this is Synthchaser from Synthchaser.com. Today I'm going to be repairing this Korg X-911 guitar synthesizer. The X-911 is called a guitar synthesizer and it can be used with the guitar, but it can also be used as a standalone synthesizer or effects unit. With a guitar plugged in, it converts the fundamental frequency of the input signal to a control voltage, which drives the VCO of the synthesizer. But it also has interface jacks on the back for providing the VCO CV directly. The customer reports two problems with this unit. First, that it's pretty obviously missing one of these buttons, and the second is that one of the presets isn't working, but he doesn't remember which one. I've picked up a few broken X911s of my own over the years that I haven't gotten around to fixing yet, and no Synthchaser video would be complete without the obligatory group photo. I'm not a guitar player, and if you've watched my videos, you'll know while I fix them, I'm not a keyboard player either. But since the problem we're fixing isn't with the pitch generator, I've got the X911 hooked up to a keyboard controller so I can test it out. I'm using this Arturia key step. The X911 predates MIDI, so I've connected the pitch CV output on the key step to the CV input on the Korg, and the gate output on the key step to the trigger input on the Korg. I did need to change the configuration of the key step via software to get it to play nicely with the X911. Normally I have my key step outputting a volts per octave control voltage and a gate signal that's 0 volts when nothing's being played and 12 volts when a note's gated. The Korg uses hertz per volt for pitch and an S trigger for the gate. So that is, the control voltage is high when no note's being played and is triggered when it changes to 0 volts. So with those changes that I made, I can play the X911 through the keyboard. The customer didn't remember exactly which preset was broken, so let's check them all out. Here's the electric bass. This is the one, the tuba is the one with the broken switch, and while the switch is missing the cap and the little springy contact that would normally be inside, I can short out the two contacts inside the switch to actuate it. So let me do that real quick. There we go. So there's tuba. I'll turn that off. Trumpet. And I think we found our problem voice, but let's check the other ones out. Distortion guitar, violin, flute. So yeah, it's the trumpet that doesn't sound right, and everything else seems to be okay. So let's, one more thing I notice playing this trumpet. Regardless of which key I'm pressing, it sounds like the pitch from the trumpet sound is the same. So that's just something to keep in the back of our minds as we troubleshoot this. So now let's go ahead and open this up and do a little troubleshooting with a scope. Getting inside is pretty easy. There's 1, 2, 3, 4, 5 screws to remove on this top panel, and then it'll just lift up and we can fold it back. So with this panel folded up, we have access to both circuit boards. The one on the top is the one that we're going to want to troubleshoot, and unfortunately the PCB layout that I found online for this is basically illegible, so I can't really find my way around from the back side of this board. So I'm going to need to release this board from the top panel and be able to see the component side. And to be able to free this circuit board, I need to take a few knobs and nuts off the front. So these larger sized pots, except for the power switch and master volume pot, those 4 knobs and nuts need to come off, and then the slider cap. So with this board released, I've put something underneath it to insulate it from the case and everything below it, and I can go ahead and I can power it on and be able to troubleshoot it while being able to see the top of the board with all the component markings and designators. Since we've got a small size synthesizer here, I thought it would be convenient to use a small sized oscilloscope. On this repair I'm using the Gochi Fix 3-in-1 handheld oscilloscope. It's got a multimeter, an oscilloscope, and a function generator, all in one portable package that you can charge up through USB. I've been trying this scope out and it checks a lot of the boxes for features that I use repairing synthesizers. The scope has a 12 megahertz bandwidth, which is high enough to troubleshoot both the digital and analog sides of a vintage synthesizer. It has measurement readouts for both the amplitude and frequency of the signals that you're viewing, and it allows for AC and DC coupling, and it has a few triggering options: auto, single, normal, and different edges that you can choose to trigger on and adjust the trigger level. It costs less than $100, and I look forward to taking it with me when I do field repairs. I'll put a link in the description of the video with a discount code that you can use if you want to get one for yourself. So looking at the schematic, I noticed a couple of things. First, the trumpet section, which is right here, it's basically identical to the tuba section, which is right above it. The difference is the tuba uses the 16-foot sawtooth rank, and the trumpet uses the 8-foot sawtooth rank. You know, there's differences in values of passive components, but it's not anything that we need to be hung up on. So we can A-B compare the faulty trumpet section to the working tuba section to track this down quicker. Second thing I notice is the distortion guitar, which is here, and the violin, which are here, are also made with the 8-foot sawtooth rank. And those are working fine, so that tells me the problem is going to be somewhere right in here. And just from a quick glance, it looks like this section contains a little envelope generator and a voltage controlled filter that uses that envelope. For all the presets, the output is tied together and winds up here at this op amp U2. So first let's check out what the good and bad output looks like at this op amp on the scope. But first I need to discuss the scope setup. A common question that I get asked when I use the benchtop oscilloscope is, how are you probing around in that circuit without connecting this ground lead? And the answer is that only works on gear that uses a 3-prong power cord and where the circuit's ground is the same potential as earth ground. The Korg X-911 uses a 2-prong power cord. So if I were to try to use a plug-in scope without connecting the ground clip, I would just see this huge 60 Hz signal on the scope. Since I'm using a portable scope that isn't plugged in on the same circuit as the device under test, this black lead will never ever be at the same potential as the device's ground unless it's physically touching it. So we always need to use both leads with the portable scope. Since I've got this board removed from the chassis and the front panel, we can't just clip the black lead to the chassis either. So there is a little wire with a ring terminal that served to ground the front panel. So this is a good place for our black lead. So I don't need to hold it. What I'm going to do is I'm going to clip this alligator cable to the ring terminal and then clip it to the black lead. And you'll notice that this little plastic clip comes off the scope probe, and that's particularly handy on the X-911 since the board is really tight. With this off, I can really get in there and probe things. So with the black lead grounded, now I'm free to probe around with the red lead and I'll get a meaningful display on the scope. But before I do that, I'm going to change this switch real quick because it's for the tuba and we want to A-B compare the tuba and the trumpet easily. Okay, so let's look at that op amp chip first for the tuba, and that's IC 2 pin 7 here. And that's what the tuba output looks like. Now I'll switch over to the trumpet and probe that same pin on the same chip. And there I'm pressing different keys ranging from the high end of the keyboard to the bottom end of the keyboard. And it's interesting because we could see the tuba change frequency as we press different keys. But what we see for the trumpet looks the same regardless of what key we press, and it looks really strange. It's like a very short spike that drifts further apart over time. So I mentioned it looks like the circuit has an envelope generator and a filter. So let's compare the envelopes between the tuba and the trumpet. I can find the tuba envelope on one leg of resistor R19, which is right over here. And I will press some keys on the keyboard. Let me get on there. So that's what our envelope looks like for the tuba. And now I'll change over to trumpet, and we'll take a look at the envelope for that. And I can find that on one leg of resistor R31, which is right over here. And the peak envelope looks a little different than the one for the tuba, but substantially the envelopes look the same between the two voices. So let's look at the output of this filter circuit at this FET here. This is TR10, and it's the FET for the tuba. So let me get in there and probe it. There we go. And while I'm probing it, it's affecting the output some, but you can see that it appears to be a 1.5 volt DC signal, but we know the audio output comes through there, so there has to be some kind of audio signal there. So let's use the AC coupling mode on the scope to separate the audio signal from the DC offset. So I'll hit the button here, AC DC. Now I can switch my scope over to millivolts mode, and maybe since we're 200 millivolts per division, we'll set the time, the volts per division as low as this scope goes, which is 50 millivolts. And there we can barely see over the noise in the scope, but we see about like a 10 or 20 millivolt peak-to-peak audio signal. So that's what we should be seeing on the trumpet as well. So let me switch now over to the trumpet and turn off the... And what is this? So let's put this back in DC mode. And volts instead of millivolts. And then we got to go down here to a smaller volts per division. So the waveform that we see here looks a lot like what we saw in the audio output, and the amplitude of this thing is all out of whack. We're expecting like a 10 millivolt, 20 millivolt peak-to-peak signal, and what we have here is this nearly 4 volt peak-to-peak signal. So probing around ahead of the FET, I think I found the transistor that introduces that spiky blip that basically dwarfs our oscillator and is driving the sound that we hear in the output. So you can see here on the scope, when I press a key, that slightly negative going blip is, I think, what's causing our problem. So what I thought was a bad transistor was actually a faulty capacitor adjacent to it. And it's this film capacitor here, and it's a 15 nanofarad capacitor, and if I test it with a meter, it's going to test okay, but basically it had developed some leakage, excessive leakage current, which I can't test on this meter, and that was causing the that clicking sound. When I replaced this capacitor with another one, that went away, but the output was still muted. And I tracked down then this faulty electrolytic capacitor, and this one we can see is bad on the meter. So this is a 10 microfarad capacitor, and I'll measure the capacitance with the meter here, and it's measuring about 7.5 nanofarads, so way lower than what it should be reading. So with those two parts changed, we now have our trumpet working. And with that, we fixed the problems that the customer asked me to repair. Hopefully you found this to be an interesting peek inside the Korg X-911 guitar synthesizer. I'm Synthchaser from Synthchaser.com. Thanks for watching, and have a great day.